We do a Quest lecture on the second Wednesday of every month, and it's a different professor from Quest speaking on their specialist topic. So it's a great way to come out and learn once a month, basically, which we love. Our December 12th Quest lecture is being delivered by Darcy Otto, and he is going to be speaking about quantum computing. Ooh, which I know nothing about, but I will. Oh, hi, Dean. Is your mic on, Steve? Is that what you're asking? Okay. Well, now that I have told you about the December Quest lecture, let's get on to the November Quest lecture. I'm delighted to have Dr. Steve Kwan here once again, and he is going to be speaking to us, as I said, about his area of expertise. Let me tell you a little bit about him. Steve has a passion for field and experiential education. An expert in volcanology, he has taught a wide range of courses in Hawaii, Mexico, BC, the American Southwest, and Yellowstone National Park. His research is focused on young landscapes sculpted by volcanic eruptions and the associated geologic hazards. One of his interests is to understand the timing of volcanic and glacial events that created Garibaldi Lake, a stunning and geologically unique local feature. He is also investigating the interaction between eruptive products of Mauna Kea and Mauna Loa volcanoes in Hawaii. Steve once worked as a science advisor for U.S. Congressman, now Senator Tom Udall. Is that Udall? Yeah, Udall of New Mexico. He has taught on the block plan for more than 12 years. The block plan is the plan that they use at Quest, by the way. Starting as a visiting assistant professor at Colorado College before joining Quest. Steve will likely be one of the few locals seen running, biking, skiing, or kayaking toward Mount Garibaldi during its next eruption. On that note, I'm going to hand it over to Steve.
evening, Whistler. Thanks, everyone, for coming. We all enjoy these landscapes in our own ways, and I'd really like to thank the Whistler Library and Jeanette Bruce and John Ray and the RMOW for allowing me to come tonight and humbly share how I look at these landscapes and some of the research that I've been able to do in these places that we all know and love, and some of us go to all the time. And so what I'd like to do is take a very complex geologic region and simplify it a bit. And the way I think of this area is sort of over the last 100 million years, we've had a series of geologic events that I'll simplify it down to mountain building, disregarding the initial 4.4 billion years of Earth history. We have mountain building, and then those mountains filling with ice, and then we have volcanic eruptions interacting with that ice, where we term that the catchy fire and ice, and then those unstable landscapes collapse. And then we're going to think a bit about at the end of the talk our future. If you need to be recentered, I have this little bar that I'm going to move across during the talk down here at the bottom. I'll spend most of my time in this talk on this fire and ice section, because we have very unique landscapes in this region that we all know and love. And so the Coast Mountain range where we live is essentially the result of compression-related uplift and isostatic rebound from deglaciation. So we have a subduction zone, which I'll detail in a little bit, and we've unloaded glaciers from this landscape, and those rocks are rebounding at about 2 millimeters per year, or 2 kilometers in the last 10 million years. And so we have a competition between uplift, where these mountains are growing, and then, of course, glacial and fluvial erosion, so rivers and wind and freeze-thaw are competing with the uplift forces. And right now, uplift is winning, so our mountains are getting bigger, and of course, we all appreciate that. The core of the Coast Mountains, most of what we see are these igneous and metamorphic rocks, the crystalline rocks that are more resistant to erosion. We have some other rocks around, but these are the main rocks that you'll see forming these beautiful landscapes that we see throughout the sea-to-sky corridor. Just a brief sort of tectonic setting. We have the Pacific plates moving off here towards Japan, the spreading center right here, the Juan de Fuca plate moving towards the North American plate. They're colliding, and that Juan de Fuca plate subducting underneath and creating the Cascade Volcanic Arch, which comes up in here into Canada. And so we have this area of collision where we have mountain building, earthquakes, volcanic eruptions, commonly known as part of the Ring of Fire. So if we look at a simplified cross-section through here, that same map view, just done in cross-section, we have spreading center, Juan de Fuca plate, moving underneath North America, causing earthquakes, potential large earthquakes, creating uplift in this area, metamorphosing rocks here as the North American plate moves this way. And then as that plate subducts underneath North America down into the mantle here, the minerals dewater, they dehydrate, and that water comes into the mantle and lowers the melting temperature of the mantle. And so that mantle is buoyant, it comes up and underplates the crust, and then we have also crustal magma chambers underneath places like Mount Garibaldi, where we've had young active volcanism in this area. So this sets up our geologic scenario under which we can have these mountains with volcanoes perched on top of them, and those volcanoes interacting with ice, and then those steep slopes falling apart as time goes on. And so we've built our mountains, and now we fill those mountains with ice. So over the last 2 million years or so, there's a little bit younger this, some surges in glaciation. We've had glaciers on these landscapes. And so we have some evidence. How do we know that there was glaciation on these landscapes? Well, the Howe Sound Fjord is a nice place to look. The southernmost fjord in North America was a U-shaped valley formed by glaciation, and then all those glaciers melt and recede, and all that water makes sea level rise and fills in that valley. And we can see here, really, really cool thing here in the Howe Sound is we go from about 300 meters depth here, and then right at Porto Cove, where you have this terminal moraine, so all the sediments pushed by the glacier in the last glaciation, you get down to like 30 meters sea level depth there. So quite a really, really neat bathymetric image of that terminal moraine here near Porto Cove Provincial Park. So nice evidence for glaciation. A little bit closer to the rocks, we have these scoured and polished striated rocks, world-class examples around this area of these very smooth rocks. If you've ever been hiking on them on a wet day, maybe playing frisbee golf over here in Whistler, you'll notice that they're quite slick and very well polished. And then we also have remnants of sediments, glacial till everywhere in the landscape that's been deposited on these materials. And so we have really, really good evidence for the glaciers that we had in this area. Looking a little more big picture at the geomorphology, the shape of the landscape, we can see these beautiful U-shaped and hanging valleys. This is the view from my office at Quest. I will remind me of that if I ever complain about my job. And we have also some of these arêtes and horns sticking up above the ice. You can see here alpha sticking up above the old paleo ice level. And so we can actually say something about how thick that ice was by simple observations on the landscape. Next time you're driving south towards Squamish, pull over at the overlook on a sunny day, and you notice a lot of these sort of rounded, sort of sensuous shoulders of the mountains in the foreground, and then you have the jagged peaks in the background. And so we can sort of put a paleo ice thickness in the Squamish Valley of up to about 2 kilometers on the back of a napkin. And so here we're 670 meters or so in Whistler Village, so we had, near 1.5 kilometers of ice above us during the last glaciation. And there's nice evidence on Whistler Peak and things like that around here to show that as well. So we've had these mountains built, we filled them with ice, and now we're going to get to the fun stuff. We're going to get to some of the real unique landscapes we have around here, where we have subduction-related and extension-related volcanism that interacts with those glaciers. And so from about 2 million, a little less than 2 million years ago, to, well, we'll see about 2,400 years ago, we've had eruptions that may or may not have interacted with ice. So here, I love lava flows. Lava flows changed my life. I had an opportunity to go get my master's degree in Hawaii, and now I get a chance to go to the big island of Hawaii with students. These are Colorado College students here, but I take Quest students and UBC students as well, and you can play with these lava flows. And you can tell I'm enjoying myself. This is why I do what I do. I try to get out there every year. Unfortunately, right now, the lava flows have stopped, and so we need them to crank back up for my trip in February. But we can say something using textures that we see in lava flows. So we have a lot of beautiful lava flows in this area. And what I'd first like to show you is here, if you have a lava flow that just comes across the landscape and stops and is cooling on the ground and is cooling to the air, sometimes you get what are called columnar joints. And if you've paid attention, or when you're in the passenger seat of a car, of course, not paying attention to the road, you'll see these on the way from Squamish to Whistler, these columnar joints. And what they are is you have a cooling surface to the air, pretend this lava isn't on the top here, this was the flow, cooling to the air and cooling to the ground. And these are cracks that form when you have cooling of the magma. So you cool and it cracks perpendicular to that cooling surface. So the ground surface is cooling here, that crack is growing perpendicular from the bottom, perpendicular from the top, and sometimes they meet and form these beautiful, nice columnar joints, these beautiful columns. We see that some places. This is from the Columbia River basalts in Oregon, but we also see here at the BC Rail Quarry, just north of Squamish, we have different features that we interpret as being formed as the interaction of similar lava flows with ice. And so here, this is in the BC Rail Quarry, we have, sorry about that, we have the cooling surface here at the bottom. So we have these joints coming up from the bottom, but at the top we'll notice that not all of them are coming straight down. We actually have almost horizontal joining here. We have nice curved joints as they come down to that cooling surface. So there must have been something going on with the cooling surface at the top that wasn't just to the air. Because if it was just to the air, we'd have vertical jointing. Bill Matthews thought, he took a good look at these back in the 1950s during his PhD work. He was then a professor at UBC. He interpreted this as these joints are curving towards a cooling surface that was ice. And so in this situation here, you had what he interpreted as sort of an esker underneath the glacier, a pre-existing melt channel. This lava flow actually took advantage of and flowed in that channel, and then took on the shape of that melt channel. And then, of course, all the ice melted away. You can also see another really interesting spot here is at the same place. And if we take a better look at this, we have joints at the bottom that are actually curving into the deposit. And then most of the joints on the side here, you can see them, they're coming out towards us. They're coming out towards this open space here. And this is the Chicamis River right down here. And this lava flow is on a hillside. There's no reason a lava flow would stop on a hill instead of flowing down into the valley, unless you had something in the way. And so again, this has been interpreted as having an ice surface here, a glacier here. These lavas came up and hit that glacier, jointed, perpendicular to that glacial, the glacial ice, and then that ice melted away, and now we have sort of a crumbling hillside with these beautiful joints. And so this gives us power when we look at other lava flows to say whether or not they were interacting with ice. And so that we'll see in some of my research, we use that as tools to say whether or not it was interacting with ice and where that ice was and when that ice was there. Again, back to the sort of volcano pornography here. Indulge me for a minute. Again, as I said, I'm a simple person, and you can see here this lava flow coming out, and it's moving towards me. I can stand there. This is a Hawaiian lava flow. They're quite well behaved. And you'll see these features on here. These cuspate ridges are giving me the direction of flow. And Mr. Big PhD can tell which way the lava is flowing because I can watch it happen. And I can say, oh, look, the smiley faces are looking at me, right? And you can see little, a cooled lava flow has these ridges on it. And so these ridges translate all the way from these basaltic lava flows in Hawaii all the way to much more mafic flows that we'll see here in felsic flows we'll see here in Garibaldi Provincial Park. And again, this is another tool that we can use to say something about how those lavas were behaving. So let's go take a little field trip and let's go up to Garibaldi Lake. Garibaldi Lake is essentially a lake that shouldn't really be there. It's perched at 1,470 meters. It's a very large lake. Hopefully all of you have been up there. Just a wonderful spot. And it formed through a conspiracy of geologic events, I like to think. So we have Mount Price here with Clinker Peak on the side. And we had two lava flows that came off the side of Clinker Peak, thought to be about 11,000 years ago. One coming down here towards Culleton Creek, but stopping up here in the high country. And then another coming down here towards the Cheakamus Valley. And this lava flow is what we're going to focus on. You can see here the pressure ridges on this lava flow telling us that it was flowing this direction. But when it was flowing that direction, the Cheakamus Valley was still full of ice. Remember, we had 2 kilometers thickness of ice in the valley, so that ice is going to take a long time to melt. And so as it's melting, the mountain glaciers were receding quite quickly, making this an ice-free zone. There's no evidence that this lava flow was interacting with ice until it filled the valley and hit the ice down here. And when it filled that valley, it stopped, and it over-thickened, and we created what's called the barrier. So the barrier is about 250 meters thick of dacite lava, and it more or less extends from here about 1 kilometer back to what is now the shore of Garibaldi Lake. And so this lava flow dammed the valley. And so that dammed valley then collected all the normal runoff, glacial melt, precipitation that should have come down to this valley, into the Cheakamus River, and down to Squamish, and then into the ocean. And it dammed it up and made this beautiful lake, Lake Garibaldi, and it also created Lesser Garibaldi Lake here and Barrier Lake here. And so we're going to take a look at these with some new technology. Bill Matthews came up with amazing ideas for how this system formed, and we're going to use some new technology, some new techniques to take a better look at this, test some of Dr. Matthews' hypothesis, and maybe come up with some new interpretations using the new technology and some new ideas we've had in volcanology over the last 50 or 60 years. So I was able to get funding from National Geographic to go out and map the bottom of Garibaldi Lake, more or less the topography of the bottom, which we call bathymetry of the lake, to see what it looks like, what's down there. So we had 2 systems, one here in the BC Parks boat that's up there. They were very, very helpful, BC Parks, and remain to be in my research. I really appreciate their help. And we had another smaller boat with more or less an amped up fish finder. So Jeff Mullins, you'll see here in a minute, drove around the lake, and sonar pinged the bottom of the entire lake, and we were able to map the bottom surface. Here's Jeff drinking his coffee. He had quite a good time. He was out there about 5 a.m. to 8 p.m. for a whole week. And I would cruise out and bring him more coffee, and we won't talk about how he relieved himself. We'll leave that. You can ask him. And we also, this is me measuring the profile of temperature with depth in the water. That way we could correct our sonar, our sound waves from the sonar, for the temperature variation in the water. And so it's quite interesting data. You get to about 80 meters depth, and it goes to 3.8 degrees C all the way to the bottom. 3.8 degrees C is the densest form of liquid water. And so pretty cold in Garibaldi Lake, and pretty deep, as we'll see. I came to be known as Captain Glass, because this is about the roughest water I would go out on in Garibaldi Lake. as soon as that little riffle would come from the breeze off the glacier, it was time for Dr. Kwan or Captain Glass to go and have a sandwich at the ranger station or make a map, something like that on shore. And so I was really, really fortunate to have Jeff out there. And Jeff did all of this bathymetry work. And so you can see here, these are all the tracks. So each one of these lines is a track. On these maps, the warm colors, the reds and yellows, are shallow, and the blues are deep. And so you can see Jeff had quite good coverage. We can interpolate between these lines. Otherwise, it would have taken way too long to do the whole lake. But here you can see I asked him, and he got me much better coverage on this part of the area of the lake. The campground at Garibaldi Lake is right here with the Battleship Islands right offshore. And so here are our results. Here's the map we made at the bottom of Garibaldi Lake. Quite interesting. This scale down here goes from 0 at the shoreline to 265 meters depth, 800-foot depth. And so we have quite an interesting morphology of the bottom of the lake. We have what we think is sort of a normal valley coming in here, a glacial valley, sort of U-shaped and relatively reasonable gradient, to a very flat bottom. And that is not an artifact of our equipment. We can image deeper than 265 meters. We can go up to 300 meters. So this is real. This flat bottom is real. And then we can sort of see this undulating plateau that kind of comes from the campground about 1 kilometer or so out into the lake. And it sort of has this toe with maybe a little bit of rubble at the bottom. And we have very steep sides of bedrock and pre-existing lava flows. So if we just rotate this model a little bit, we can just see from a couple of different angles this sort of normal valley, as we'll call it, here, and then this interesting plateau that comes around here looks an awful lot to me like a lava flow. And you can see right here this sort of deep line going through here is the contact between bedrock, the rock that was there before the lava flows, and the lava flow. And that becomes an important part of our story as we move on. So if we fly back to the barrier here again, we start to think about what might have happened. What can we say about this system from our new data? So again here, just to orient you, Mount Price, Clinker Peak up here, this lava flow coming down, hitting the ice at one point. And you can see here it built its own levees. Lavas build their own levees. But it had breakouts through those levees. So I would say this is one lobe here, and another lobe here, and another lobe here. And it looks like this lobe actually, as this flow came down, it got pressurized, and this lobe actually started, based on the pressure ridges on land, started flowing this direction. And so we were able to get a higher resolution sonar data set as well, just for this area right in here that Jeff mapped in great detail. We sent the other boat there, and we'll see in a second some results from that and try to interpret them by saying, if we look at these, we can say that those look an awful lot like pressure ridges. And so the warm colors, the greens and the yellows, are shallower water, and the blues are deep. So if you look at the pressure ridges sort of on this flow, these beautiful pressure ridges here, they sort of are the same size and wavelength and magnitude of the pressure ridges on this lava flow that was flowing this way, which is quite interesting because you would assume it seems like it's in an uphill direction. But it was flowing into this very flat-bottomed paleo valley, we think. And what we're able to do is get a bit more of the dynamics of this system. Which lava flow lobe came first, and how did this whole barrier Garibaldi Lake system form? And this new technology has allowed us to look underneath the water and say something about what lava flows were going which direction. And so we got this data, quite happy with it, and we said, well, we have these smaller lakes that are quite dynamic as well, Barrier Lake, Lesser Garibaldi Lake, and we want to check those out. And so I was thinking, how the heck are we going to do this? We don't want a big boat out there. It would take about 2 seconds to get across the lake, and we'd ram into the shore, and that probably wouldn't please BC Parks. So I called up Kahuna Paddleboards here in Whistler, and they were very generous and donated to me for this research a stand-up paddleboard that comes in a backpack with a pump and all that sort of stuff. And I drilled a hole in the fin, and I mounted my sonar transducer to the fin, and the cable runs up there to this Pelican case, where you have the brain of the sonar system and a battery, and then you just paddle around, turn this on, paddle around, and collect. You can map the bottom of the lake. And this is my current student, Martin Lentz, who he and I were up there in August doing some mapping on Garibaldi Lake and Lesser Garibaldi and Barrier Lake. And so Martin is a very active guy. You see him skiing around here and going to the hospital and then recovering and coming back. So I think this is a new sort of later in life activity for you, Martin. he didn't sustain any injuries that I knew of. And I had him out there early in the morning, and he was day, noon, and night, and we kept expanding the amount of ground we wanted to cover doing this. And he got quite good at paddling, and I think by the sort of smile on his face at the end of the day, he quite enjoyed being out there. I think he enjoyed being out there, especially alone. I would come out every once in a while on paddleboard if the water was calm, of course, and see how he was doing. But he collected excellent data. He just presented his research at the Geological Society of America conference in Indianapolis. Quite a successful poster presentation. But he got really good at paddling. He's amazingly fast now. It didn't affect the quality of the data, his wake or anything like that. As you can see him cruising around here, these are the Battleship Islands. The campground will be just off here to the left. And he covered quite a bit of ground, and we had a very successful trip in this beautiful place. And I'd been paddleboarding once in my life, and I wasn't sold on it until I got that Kahuna paddleboard. Remember, Kahuna paddleboard, everyone. And so here are some of Martin's results from Lesser Garibaldi Lake. This is 27 meters deep here is the blue, and of course the shoreline in red. And what we're quite interested in, it's kind of a bowl-shaped lake with steep sides, and then we have this interesting undulating plateau here at the southeast side. And as we sort of rotate this model around, we can sort of start to get a look at that, where we go from shallow to a little bit deeper to shallower to a little bit deeper, and then we have again a toe on that's quite steep. And I'm just going to enhance the vertical exaggeration to point that out a little bit more here in a second. And you can see that we're starting to interpret that as a lava flow, where we have these pressure ridges from a lava flow coming in and then again stopping. And why wouldn't that lava flow fill in this pre-existing low? And we'll think about that in a second with some of Martin's interpretive results. And so the bedrock contact is coming right through here, through the lake. Turns out when you make videos on your computer and you have music in the background, it records everything. And so let's think about Lesser Garibaldi Lake here, right here, and why this lava flow was coming down. It's going to fill this valley. Why didn't it fill that depression? And so we're going to rotate around a little bit here. We can see that the lava flow came down, broke out here, made the big plateau in the lake. This would have come after that, where it runs into there. But you can see that there's quite a high here at the edge of the lava flow, and then it comes down and it doesn't fill in that depression right behind the barrier. And so we've been thinking about this and how could that have happened. And what Martin has concluded, or he's going to conclude when he makes up his mind, is that there were likely stranded icebergs. So we had this valley full of ice, and we probably had some icebergs here at Barrier Lake, which has a similar sort of deep bowl-like depression with a very steep-sided lava flow, and here at Lesser Garibaldi Lake, where you had these lava flows coming down. They came down, they breached the levees coming up here, but they wrapped around these depressions. A lava flow should go into that depression. So what Martin thinks happened is that the lava flow came down, and you can see sort of pressure ridges here, and we'll get a little closer. They come into the lake there, and he thinks that there were icebergs there that stopped those lava flows. There was enough time for them to stop and solidify before that ice melted away. So now what we have is lava here. We have the creek coming out of Garibaldi Lake, and we have bedrock on this side. And so the contact between the bedrock and the lava goes right through Lesser Garibaldi Lake. It goes right through Barrier Lake. And it seems to be that this lava flow wasn't able to get all the way over to that contact because there was ice in that depression. And so now we think about this entire thing as a hydrologic system. How is this whole system behaving? We have Garibaldi Lake that fills up. It overflows. When it overflows, it fills up Lesser Garibaldi Lake. When that overflows, it fills up Barrier Lake. And we also have that water seasonally going up and down quite a bit. And so we'll think about what's happening there. And this bathymetry is really helping us because we can get a very accurate volume for the lakes. For example, Garibaldi Lake's volume is about 1.2 trillion liters of water. And sort of, when I put that in context for my students, that's 3 trillion cans of beer in the lake. And so here, let's go from the lake and think about this as a system. We have Rubble Creek coming out from the bottom of this lava dam. So the barrier, we can think of it as a lava dam going back here. and we have Rubble Creek that comes out from the bottom of that dam. And essentially all of this water is just springing out from below that dam. There's not very often do you get overflow over the dam to join that creek. That only really occurs during extreme precipitation events where you have a waterfall over the barrier. And so let's go down to Rubble Creek. It's quite an active area. It's an exciting place to be. If you can see it here at the top here in a second, you'll see boulders trundling down the slope and leaving dust plumes. You can see one right there. It's quite an interesting place to be. It's a little eerie to be down at Rubble Creek with this very unstable barrier. And you can see the rest of the rock wall back here and all of this scree. And so this water is just raging in these springs out of the bottom of the barrier. And it's constant. It happens all year round. And as we'll see in the data, it's more or less consistent all year round. And so what I've done over the years with BC Parks and with students is put some monitoring equipment in here. This is a measure of lake level at the new dock they built a few years ago. I also have one at the bridge that you cross over when you're coming on the trail to Garibaldi Lake. And I had one in Rubble Creek until we went down there and couldn't find it. And we did a little forensic analysis. Leslie, Anthony, and I were out there. And we determined that a landslide came and washed across the creek, buried my sensor, and never to be found again. But we do have some data that we recovered from it prior. And here is some of that data. So what are we looking at here? Well, on the y-axis, we have stage. These numbers, don't worry about too much what they mean. Just think about higher stage means higher level or higher flow rate, and lower stage means lower lake levels or lower flow rates. And so the blue is the Garibaldi Lake at the dock. And what you can see this is from July 2015 to just before freezing in November of 2015. And you can see the lake sort of fills up in the spring, and then you have a big precipitation event, fills up, and then it sort of undulates throughout the season, and then towards the winter it starts draining. The overflow creek, as you can imagine, as the lake fills up, it's going to overflow more, and so we more or less track that data where the overflow of the lake is showing the lake level, and that makes perfect sense to us. We're pleased to see that. This gray data down here is from Rubble Creek. What you notice about Rubble Creek is quite consistent throughout the year. This blip is from a big precipitation event that is shown here where you had 100 millimeters of rain in 28 hours or something like that. And so you had water cascading over the barrier and affecting the flow rates in Rubble Creek. But otherwise, we have quite a consistent flow in Rubble Creek. It's not really affected much by what's going on in the lakes and the overflow above it. And so we started thinking, well, where is all this water coming from? We have about 3 cubic meters per second of water coming out of Rubble Creek throughout the year. And it seems to be just springing out from underneath this scree. There's a series of springs here, and just out of range over here, there's another 5 or 6 springs. This is bedrock over here, and those springs are actually some of them right on the contact between the bedrock and the lava flow. And so we're thinking, okay, how can we monitor this? How can we figure out how this lake is behaving? And I have a lot of long drives on these field trips that I run with my students. And Madeline Martin and I were sitting in the front seat and started chatting. And she had the brilliant idea of, in the summer, this lake is quite dynamic. You have all sorts of uncontrolled inputs. If it rains, you have input. If you have glacial melt, you have input into the lake. And so it's really hard to control, even though we can monitor it, to say how that lake is behaving, because we can't really quantify all of the inputs. So she said, well, I've skied up there, and in the winter, of course, it's frozen. That lake is frozen, and everything around it in a normal year is frozen. And so we can more or less assume that the input into the lake is 0. And so we can think of this as a frozen top system where we can see, is the lake draining into Rubble Creek in the winter, and we can quantify that rate, because we don't have to worry about the data going crazy as water comes in from every which way. So her idea of looking at this frozen top winter system was quite amazing, and so she went with it, and she did her project up there where she rigged up this system where you have a buoy and a dry bag at the surface with a cable and a rope going down, a few corks in there to keep it all level, and then she had a PVC tube with a data logger in it, just like we have at the dock. And so she'll complain, she's probably still complaining even after graduation, about carrying this anchor up to Garibaldi Lake in her backpack. And so it was this sort of angle iron to keep the whole thing sunk at the same level. And so the amount of water over this gives you a sense for how much water is in the lake. What is the lake level doing over the winter? And then we can say something important about the lake based on those measurements. So this is her data. Again, stage is going to be the lake level. You can see here from 0, the lake level is going down on the y-axis. And this is from February 2017 to May 2017 when things started to melt, and she took the sensor out. All of the blue dots are her data points, and you can see that's quite a linear decrease in the level of the lake, and she was able to fit a linear equation to this. And when you fit equations to data, commonly it's very messy. If it's a perfect fit, you have an r² value of 1, and she has an r² value of 0.98. And an ecologist gets excited when they have an r² value of 0.5. And so I said, well, students, you should become physical scientists because our data is straightforward. And so what she's able to do is fit this equation here, and now we have the volume of the lake. And so she said, well, if I'm losing this much of that volume, I can convert that into a rate. And so she calculated that from Rubble Creek, or from Garibaldi Lake, the contribution to Rubble Creek over the winter is 1.7 cubic meters per second. So again, remembering that all these springs combined are 3 cubic meters per second. And so she didn't solve the whole problem because we still have water coming from somewhere else, contributing to this system. And so we have to do a bit more research. And looking at this system, it's quite a fascinating system. We're thinking about other ways to measure that water, but we also have the 2 other lakes, Lesser Garibaldi Lake and Barrier Lake. And perhaps those are the contributing factors. And so Martin Lentz, after he did the bathymetry and got the volumes of those lakes, we're going to get permission again from BC Parks to sink a logger in Lesser Garibaldi Lake. So if you see a buoy there as you're skiing across this winter, just let it be. I just want to point out here, as Rubble Creek goes down past the parking lot and into the Chicamus River, this is what's called lobe 4 of the barrier. And if we just take a little closer look at lobe 4 of the barrier, we can see all these little dots on it, and those are all joints pointing out at us, showing us that this part of the barrier was indeed in contact with ice when it formed. And so this is what's thought to be the most unstable part of the barrier, and as we talk about collapse later, keep that in mind. This is what BC Hydro and people like that are monitoring for potential landslides in the near future. So we've done a good job of looking at Garibaldi Lake. Still lots of work to do, but Garibaldi Provincial Park is an amazing spot. And I want to go to some other places up there. And so I want to look at, we have Garibaldi Lake here, and as you gaze across the lake, you sort of say, well, what the heck is this thing? It's flat, Mount Garibaldi behind it, but we have this flat-topped mountain. We learned that's called the Table. And so the Table was studied by Bill Matthews in the 50s, and he had an amazing eye for textures. And so what he interpreted, probably in a canoe and on horseback and that sort of thing, not in a helicopter like we got permission to land and get dropped off on the top here, he interpreted this as a tuya. So a tuya is a subglacial volcano, and he interpreted this as a stack of lava flows, one after the other, that essentially made a cauldron in the ice, melted a cauldron in the ice, and then stacked up to where then it breached the ice and have a lava flow on the surface, because you can see here this red rock is oxidized, so we thought it was exposed to the atmosphere. Well, we decided to take a closer look at this using some new techniques. This one is photogrammetry. This is a picture of us looking at of the Black Tusk, and this is Alex Wilson. It's actually his good side, and you'll thank me for that. Taking pictures of this, and so we fly around in a helicopter, in this case, and we take a bunch of pictures of an edifice. This is Mount Phi, a model we made of Mount Phi this summer, just as an example. And what the software does is you upload all of these photos, and it knows where the pictures are taken from, and it does this point cloud. So all of these blue rectangles are photos, and that's the vector is the direction of those photos. And so the software is quite amazing. It overlaps all these photos, and it builds a mesh for the landscape. And then it builds sort of a dense point cloud, and then a triangular point cloud here, and then it drapes the photos over that mesh, and you can get quite a high-resolution model of this edifice in a day. So you might fly in the morning, you can load these up at lunch, and let the computer churn through, and you can get sort of a medium-resolution model here so it doesn't crash my computer in a day. And so this is just an example of one of these models. This is Mount Phi. And I just love Mount Phi. When I moved to go to UBC for my PhD in 1999, I was driving north on Highway 99, and right when you come over and crest and go down into the canyon, you see this part of Mount Phi. And it looks an awful lot like one of my future funding sources and equipment. That I've heard they've just rebranded, so luckily I caught this image. But next time you're heading north, you'll see it on a nice sunny day. It is perfect. It's this part of Mount Phi here, and it was a joy to fly around Mount Phi and check this out and make this model. We're working on a bunch of models of these mountains across that you can see from the top of Whistler to interpret the glacial volcanic history. So that shows you one of the new techniques we're able to use, and we made a model of the table. And we sort of have an advantage over Bill Matthews. We don't have to creep around the sides and stumble on the scree. We can sit in our air-conditioned offices and rotate this model any which way and get new vantage points. And we start to see these things like these ridges on the side. And we were able to land on the top and take a bunch of drone images of the sides and sort of get high-resolution look at these things from up close. And we see on this mountain, we have jointing everywhere that's sort of facing out towards us. And you can see it in a high-resolution model. We can also rotate this to look down at the top. That's pretty hard to do from the ground. And we start to see these sort of elongate structure. The tables elongate. And it has these fins that are sort of running with that elongation here. And in those fins, all sides of those fins are jointed. So they show us that they're primary contact surfaces with the ice. And so we can see inside of all these gullies and little convex and concavities, we have jointing. And remember that jointing is showing us we had primary contact between lava and ice. So we have a new model for what we think was happening to form the table. And this is just coming out in the American Journal of Science. We just sent in our review. We got the reviews back and sent the final version yesterday, actually. Quite excited about this. And so instead of this material coming up and forming lava flows, stacking up, what we think is we have the basement rock. The table happens to be on a hill. And when that dike came through that crystalline basement and it intruded into the ice. So the magma, the lava, is coming up and intruding into the ice. And of course, it's going to melt some of the ice. But lava is a very good insulator. Rock is a very good insulator. So as soon as you get a carapace of breccia, which is a broken up lava on the outside, it will insulate you from that new lava and the ice so that it won't melt all the ice immediately. Another advantage of this sort of model is that you have almost immediate draining of the meltwater. So it's melting the ice, and that water is able to drain right out because we're up on a hill. So as we continue to look at our conceptual model, we think this is an endogenous growth. Exogenous growth would be lava flows building on one another. What we think happened was you had the dike come up, intruded into that ice, and you kept that surface, that ice contact surface, and then the next dike came and intruded into the middle. And so this whole thing started just expanding out rather than building vertically. It was already tall vertically, and it's expanding horizontally. And we start to see marginal dike injections with these textures that we see on these concavities and convexities here in map view. And so we were able to use this textural evidence to reinterpret the table and say what we think was, instead of these being lava flows that we think Bill Matthews saw from reading his papers, he thought these were sort of evidence for lava flows. We think they're anastomosing dikes and sills. So the last gasp of this eruption, you had the mountain was there, and these dikes came up and sort of wormed their way through. And we have additional evidence of the jointing on these dikes that they're in place post all of this other stuff. So they show sort of internal cooling histories. And so we have a new interpretation for the table. And so that's quite exciting, and we're really happy to get that paper accepted. So here, as we sort of see across the table here, we're going to check out another spot in Garibaldi Provincial Park, and we're going to think about reinterpreting this spot. Now, we haven't published it yet because it's a little more high profile in the literature, and also because you can see it from up here at Whistler Mountain. And so, excuse my drunk flying here, yeah, we turn around and we see the Black Tusk. And immediately we start to see things in the Black Tusk that start to look like things we see in the table. So let's just make some observations here. So as we look up here on this, you start to see those joints are pointing off into the sky. You can see the joint orientation is like this. And they're sort of pointing to that old cooling surface, which would be off into the sky now. So you might interpret that as being ice. If we look at this material right in here, we can see those joints are vertical. So they maybe weren't interacting with the ice. And we start to see that material is anastomosing right through this pile of volcanic material. You can see it go up to here. You can see it come curving around up here. You can also see that sort of dike and sill network curving around and coming down here. And so by an interpretation of all of these structures, we're starting to put together a nice picture that the Black Tusk might have a different formation than we think, and we think it might be a very similar formation to the table. The Black Tusk is thought to be about 220,000 years old. We just got a new age for the table at 100,000 years old. So it's a little bit older than the table, and we'll see some effects of that as we look at our 3D model here in a second. But you can see that these dikes are sort of anastomosing and branching off and coming all the way up through, and you'll see eventually they'll sort of breach out at the top there. And so exciting new interpretations for what might be going on at the Black Tusk, and we're looking forward to sort of sitting down and getting more detail on this model. And so the pre-existing model for the Tusk Formation was you had a cone of volcanic cone, or you can think of it as a volcano, and that this was thought to be the core of that volcano, and the rest of it has eroded away. And so the hypothesis that was put forward by Bill Matthews and then Nathan Green was that this is the sort of the core, the more resistant rock of that volcano that's not eroded away because it's hardier. And we're reinterpreting that. And we think that when we sort of look at this 3D model that we made, we start to see things that are very similar to the table. So we're thinking of reinterpreting this. We start to see these fins, and all of these fins have these features, again, using these textures in the lava flows to give us leverage on determining what happened, what were the dynamics between the lava and the ice. And here again is our area where we have that dike running up through, anastomosing up through, looking very similar to the table. And I should rotate to get a vertical view here in a second, and you'll start to really see those fins come out and the elongation of this. And it looks like a dike. And so you can see here these fins are running, again, lengthwise of this dike. And the evidence, the textures on these fins really give us a sense for there was a lot of this is still primary material that was in contact with ice or very close to being in contact with ice. And so here, let's just circumnavigate the Black Tusk, which we had a great day doing. And you can start to see that here we have some really nice jointing heading off in this direction, probably ice contact jointing. And we have jointing that's running up through here vertically. And so as we start to look at other pieces of the tusk, looking up close here, these are joint sets with these sort of fracture sets going into the screen that are very common in the literature for ice contact volcanism, primary surfaces of lava interacting with ice. And so again here, just cruising around, we again see jointing going in almost every direction, and we can start to reconstruct the paleo-ice surface. And so science is sort of depressing to do. It's all about testing hypothesis and trying to prove yourself wrong or prove others wrong in this sense. So we're going to wait. We're going to put our hypotheses out there, and my students can then prove them wrong when I'm retired and paddleboarding every day. And so we've been through the fire and ice, and now we're going to move on a little bit to think about these very unstable structures. They collapse. Gravitationally, they're unstable. You can see them. They're interacting with ice. There's all sorts of joints and fractures in them, and so they like to collapse. And so we've had some pretty major collapse events in the recent history. This is just one example, a map of the barrier. So there was a major event in the winter of 1855. They're not sure if it was 1855 or 1856. And the fan deposits, so the barrier is right here in red, and it unleashed quite a bit of material, came down, and it would have covered what is now Highway 99. It would have dammed the Chicamus River just like Daisy Lake Dam is there now. And so this is certainly a controversial area. A neighborhood was moved from this sort of hazard zone. The provincial government moved that area. So it's quite interesting. A lot of research has gone into the stability of the barrier and the unstable volcanic slopes. Remember I talked about lobe 4 showing all of those ice contact textures? Well, that's what people are most worried about, because the other part of the barrier, those ice contact textures have fallen into the valley, but lobe 4 still shows those primary textures. right up here is lobe 4. And so those primary textures are thought to not have collapsed yet. And so that's where most of the monitoring is going on. BC Hydro does monitoring. SFU has a postdoc doing some monitoring in UBC as well. But I want to talk about another big collapse event that has to do with sort of volcanoes in this area. So we're going to go a bit north. We're going to go from Garibaldi Lake, and we're going to go a bit north here up to Mount Meager. Mount Meager is a bit of a rock star right now in the news. The CBC did a nice article and subsequent radio show on it. And Glenn Williams-Jones from SFU is heading up a crew looking at Mount Meager. And this area is quite unstable. It's a sort of a rotten volcano. It last erupted 2,400 years ago. Fantastic pumice deposits. If you've ever been over to the Chilcotins, you see pumice everywhere on the mountain biking trails, and that's all from Mount Meager Massif. This scar right here that goes both ways in this valley was a huge landslide in 2010. And so this was one of the largest landslides in British Columbia history. It was about a month after I moved back to British Columbia, and the volcano that I'd been studying, partly in grad school, started falling apart. And so this was the Lillooet River, and this is about a month and a half after the landslide. You can see just complete devastation. And this landslide released from up here, came down the valley, you can see the scar there, washed through and destroyed everything, including the bridge over to the hot springs. And it also was so fluid, it went up the valley quite a few kilometers to where the beautiful old hot springs was. And so this is an example of the interaction of ice. So they think the landslide was melting of the glaciers on a hot day, loading these unstable volcanic slopes and overcoming the strength, and then due to gravity, a heck of a lot of material releasing down into the valley. And so Pemberton being downstream, this is certainly a hazard that people are worrying about. That's not the only thing going on at Mount Meager. And so let's think about our future in this region. And I'm just going to wrap up with some pretty exciting stuff that's going on at Mount Meager right now. We had the landslide, 8 years ago, and now we're starting to see some activity that has recently been recognized. So this is an ice cave, or a fumarole. So this is about 50 meters deep, it's about 30 meters across, and this is steam coming out of this cave. And the first sulfur smells were reported in February of 2016. That doesn't mean that's when they started, but that's when they were reported. And before that, from 2011 to 2016, there were a bunch of magnitude 1 to 2 very small earthquakes in the vicinity. Now, because there isn't a lot of volcanic activity in Canada, we don't have seismic stations on the volcanoes. They're getting them up there now to see if this was actually from volcanic activity or not. Glenn Williams-Jones at Simon Fraser was just up there, and he's been measuring the gases. He measures gases at volcanoes, and he got 280 parts per million of H2S and 2,700 parts per million of CO2. Now, don't go up here and go into this cave, because it's a cool spot that I showed you. This is, this could get you in trouble if you're in an enclosed area. It's, for a volcanic eruption, it would be quite low. So I'm not saying that Mount Meager is starting to erupt and there's earthquakes and all this sort of stuff, but there is some activity up there. These are elevated relative to background, but just to give you a sense, you'd have about 10,000 parts per million if it was fresh magma being intruded into the subsurface. So Glenn is working on putting new monitoring equipment up there, and we're going to go up periodically to see what's going on. These images, on the left is a sort of a camera from a drone, on the right is an infrared image on the drone. These are a couple of people making gas measurements down here. What you can see is the warmer colors are, of course, warmer, and these are the same fumarole, just at different zooms. And so you can see that these fumaroles are elevated temperature relative to the surroundings. And these are just rocks over here that were warming up in the sun. So very exciting stuff going on up at Mount Meager. And it sort of makes me ponder what's going to happen in the future of this area. Sure.
A few years back, we had this big panic about when the big one goes. In other words, when Mauna plate.
Mm-hmm.
What's going to happen to our area when that thing slips?
Okay, so a question about what is concerned about the mega thrust earthquake, right? This big 9.0 earthquake, similar to the one that happened in Tohoku, Japan, causing the tsunami and all of the nuclear reactors melting down and that sort of thing. So the question is, what might happen in our area? Well, let me see if I am really prepared or not. Probably not. Nope, sorry. What I had was a diagram of the probability of one of those big earthquakes and when they're going to happen. And so they think it's every 200 years or so, and we're quite due for this. But what is interesting is that you worry about things like the barrier collapsing, or big parts of the barrier collapsing, but the barrier has been through a number of those earthquakes in recorded history. And so I think in terms of a catastrophic failure at the barrier, probably not going to happen. But liquefaction of soils in Squamish on the estuary and downtown, things like that. I think we're fortunate to have very high quality building codes around here, so it would be a pretty wild event with shaking. But I think probably south of here, Squamish, Vancouver, Delta, Burnaby, with the soils are probably going to be where the most amplification of those waves is going to happen and the most damage would probably happen. Yeah.
What's your sense of the integrity of the north slopes of Meager versus those eastern slopes that flow down into Capricorn?
So the question is, what's the sense of the integrity of the north slopes of Meager versus those eastern slopes that flow down to where the landslide was in Capricorn, right? I think that the Capricorn peak is notorious for being really rotten, and so it probably had a fairly long-term hydrothermal system, hot water steam system running through it, and just baking and destroying that volcanic rock. One of the issues is a lot of those northern slopes are, of course, covered in snowpack and glaciers, and so in going up there, sometimes there's very competent crystalline rock that's sticking out, which would make us think that it's going to be quite stable. But in the opening video, the slope up to the left is quite unstable, and it's actually moving. I can't remember, Gio as a PhD student at SFU, it's actively deforming, especially in the summer when it gets loaded with snowmelt. And so he would argue that slope is the next to go, and he can tell you exactly how much he thinks is going to go as part of his PhD research. So part of it is what we can see, we can say more about, but the stuff that's underneath the snow and ice, we'll wait for it to move. Yeah.
The Rubble Creek, the water that's coming out of that slope, is that cold or hot water? Is that thermal water?
Right. So the question is the flow coming out of Rubble Creek. We measured the temperature, and it varies between about 6 and 7 degrees Celsius. So it's cold, relatively cold water. And so a rule of thumb is that, I learned this from my hydrogeochemist friend, is that the average, so for groundwater, it will give you the average temperature in the area as a rule of thumb. And so if you think about that area, 6 or 7 degrees sort of over the year would be maybe about average. So we think it's groundwater. So it's not being heated at all by a volcanic system, and it's just water that, at least part of it we know, is coming from the bottom of Garibaldi Lake, which would have been at 4 degrees Celsius, and so it's heating up a little as it probably slowly moves through that system. Yeah.
Is there danger about a seismic event that's not from an earthquake, but from a mechanical failure of any mountainside? Like in Pemberton, they're worried about washback from a mechanical event, but us being like Delta, being on wet clay, there could also be seismic waves from a mechanical failure of Mount Curry. Is there anything around here that not just a debris going downriver and creating damming and flooding, but of inducing a ground wave that's like an earthquake?
Yeah, so the question is, could we have a seismic event big enough from a landslide to sort of create the same hazards that we might get during a large tectonic earthquake? And I think those seismic waves, while they can be seen and felt, they're just not of the magnitude. And they're just going to be those surface waves. And so I don't think, unless quite locally, you would have where you would already be in the debris path or something like that. It might magnify some effects, but I don't think that those waves are going to travel far enough to cause any of these other concerns. But the Earth surprises us. Yeah, in the middle.
So your research is focused on a very
Right, so the question is, I look at quite a small area here in Garibaldi Park, and what have I seen elsewhere in the world that have been glaciated? I haven't yet been to South America, but Iceland, if you've ever been to Iceland or ever get a chance to go to Iceland, this is like geotourism in Iceland everywhere. People go and they see there's all sorts of cool subglacial formations that they have columnar joints in downtown Reykjavik, and it's sort of part of the culture, these subglacial eruptions. There's lots of pillow basalts, so when these eruptions happen on a flat surface and they erupt they make their own lake, they sort of form these pillows that only form underwater. And then you get a stack of that, and you get a stack of fragmental material, and then you can see dikes going up through it. And I went there on a geology field trip, and it was a spectacular place. So BC and Iceland are sort of the main places where we see these tuyas, these flat-top mountains, and the subglacial evidence for subglacial eruptions. And what's cool about Iceland is they're happening still there as they erupt under the ice, and we can see how the ice is deforming. And one of the neat things that we reference in our paper is that they can actually image dikes in the ice. And so we know that that's physically possible, and it's happening in Iceland right now. So Wells Gray Provincial Park in British Columbia is another spot that has a lot of these subglacial. But they're quite rare in the world. Yes?
On your opening picture, the fissure that was fuming, is that meager?
That's Mount Meager. So if I can go back here for a minute. So the question was this fissure that's fuming. These are fumaroles at Mount Meager, and the opening one was as well.
The opening one, so
Yeah, there's 3 of them up there. Sorry?
so there's still heat activity happening at Meager?
Yes. So this was these drone videos were September. Yeah. You guys were up there? September. Yeah. So it's active.
So is there still activity, some heat activity from Dalton's Dome area there on Garibaldi?
So the question is, there's still heat activity from Dalton's Dome and Mount Garibaldi. And it was quite interesting. This summer, there was a lot of what looked like smoke plumes up there. And it turned out to be wind events that were churning up the fine ash material. But you could see it from downtown, and it's like, oh, finally, it's happening. Let's go. But I think that there's sort of a lot of snowmobiling in above Cat Lake there, and you hear sort of these rumors of fumaroles and melting through the ice. And I'm keen to go and check that out as soon as somebody donates a snowmobile to my research efforts. So if anyone knows or has, or yes.
The depth of Garibaldi Lake, you said
265 meters deep, Garibaldi Lake.
didn't really explain, that's incredible.
It's incredibly deep, yeah. Yeah. So you want me to explain it? Yeah. Damn it. Well, maybe you can explain why there's a flat bottom in this old valley. So what we think is going on there, if I can get back to one of the maps here and stall and try to think of an explanation. Getting there. Almost. Got to get the perfect one, of course. Okay, so here we go, right? We have this plateau or lake bottom at 260 meters depth. And so I think what you're looking at is you just have a really steep-sided panorama ridges right up here, and those are really steep-sided valley, and another steep-sided valley coming down here. And I think the reason it can be so deep is that this lava flow is really thick. It's much thicker than it would be. Because it butted up against the ice here in the valley, Paleo Valley, I think it thickened so much that it essentially filled in that valley, which allowed the lake to be deep behind it. So a normal lava flow would be maybe 30 meters thick, and so this is close to 300 meters thick. And so I think that's really what happened there, is this valley would have been sort of a plateau and then probably steeply going down towards the Chicamas. And I think it's just because of that over-thickening of that lava flow allows this big basin to fill up. So it just created a huge basin and a heck of a lot of water. Yeah?
Just related to that, is the depth of the bottom of the lake the same?
That's an excellent question. So is the depth of this, the elevation of this, is it the same as where it's coming out at Rubble Creek? Sorry? Yeah, Rubble Creek's a bit lower, but it's a reasonable slope to think of it being along the contact in the valley down there. So you can sort of, what we're starting to do is trying to remove this in GIS on the computer, sort of remove this lava if we can, and reconstruct the old valley and see if that, is it a reasonable slope that we're dealing with? And so we try to reconstruct, is that normal groundwater flow, and how long would that take, and how much water is in there, and certainly an ongoing project that's quite exciting to continue. Yeah?
Just real quick, that's pretty unique to have a lake exit underground.
Yes, so it's pretty unique to have a lake exit sort of underneath the dam. I don't want to be an engineer, I never will be, but I think an engineer would say, unless you planned it that way, bad. Yeah, yeah. Yeah.
So the drainage, which from Garibaldi Lake down to Lesser Garibaldi Lake and Barrier Lake, it comes out at the top up there. But it seems to be on the south side of the barrier coming out of Rubble Creek. This other point here seems to have possibly an underground drainage up there also.
Right, so what we're trying to find is we haven't gotten all the drainage yet, right? We have half of it, a little more than half. So now Martin's going to figure out where the rest of the water's coming from. Yeah.
So you don't show any flow going down?
No surface flow.
No.
Yep.
What is the question? You couldn't hear.
Oh, sorry, she was asking about different subterranean flows, right? Different subterranean flows to Rubble Creek rather than just from Garibaldi Lake. And so we think they're coming from the other two lakes. And what you'll notice is in the winter, those other two lakes drain quite a bit. Almost totally drain Lesser Garibaldi Lake. It'd be quite interesting this winter to see how much, if we can quantify that. Yeah?
Is the flow that is out of Garibaldi Lake accounted for in the creek that goes out?
So the question is the flow that the overflow coming over here, is it accounted for in the Rubble Creek?
Well, the amount that you lose out of Garibaldi Lake itself.
Oh, right, so the amount we lose out of Garibaldi Lake itself. When, in the winter, the reason that Madeline did this work in the winter is because this doesn't overflow in the winter. And so we can essentially say there's zero input and zero output on the surface, and then everything is in the subsurface. So that's why it was key to have that frozen top system. Yeah, so we essentially account for it by eliminating it. Yeah?
What do you know about the structure of that particular lobe there?
This
Fracture, is it impermeable?
so the question is, what do we know about the structure of this lobe here? Is it fractured or permeable? And so if we look at other lava flows in the area and we can find the contact between the lava flow and the ground, we see almost always that there's a rubble at the bottom of these lava flows. So it cools very quickly to the ground. It's a process called autobrecciation, where it breaks itself up and churns over the top of it. And so the base of lava flows are commonly porous and very permeable. And it's a really nice place for water to flow, is groundwater to flow. So it's sort of, our hypothesis is that that zone of brecciation and permeable rock is where this groundwater is flowing through. Yeah, so the question is, he's been to Iceland recently and noticing differences between these volcanic rocks in color and shape and this sort of thing. And so the question is, different parts of the world, do they have different magma behaviors? And here we have, when you get into the nitty-gritty of it, the chemistry is a bit different. But I think what you're seeing is just different interactions between the lava flows and the ice. And so in Iceland, most all of it is under the ice with water involved. And fantastically, in British Columbia, most of our eruptions that were under the ice happened on high points. And there's some work going on to figure out, is that preferable for an eruption to happen on a high point? But the reason that things will start looking differently is those high points allow that water to drain. And so you get quite a different look to the lavas when they're sort of drained rather than erupting into the water. So that's part of the reason.
I have another question to that. Does this climate change affect deglaciation equally, like in BC and Iceland and everywhere else? Well, I don't really know if it's totally.
Yeah, so the question is, does climate changing affect the deglaciation in different parts of the world the same? And I think overall, you can sort of say, yes, most of the world is losing glacial ice, but then you have microclimates and sort of local effects that can change the amount of ice that's lost or whether or not glaciers are going to grow. My favorite example is the only glacier that's growing in the lower 48 United States is in the crater of Mount St. Helens. And so Mount St. Helens stopped erupting in like 2008 or something, and there's these lava domes there, they're steaming away, and there's a glacier that's growing and more or less coming around them. I went in there a couple times with field trips, and each time it was several tens of meters of growth. And what happens is the snow blows over to that north-facing bowl, and it's shaded all the time. So it's quite interesting. So you'd have to say that's sort of a microclimate that's causing that glacier to grow that's unique to that area. But in general, I think the warming is reducing ice globally. Yeah?
The table and the Black Tusk being 100,000 years apart, did they form the same glaciation event?
So the question is, the table and the Black Tusk are about 100,000 years apart, and did they form in the same glaciation event? And I wish Alex Wilson was here. He's doing his PhD on just those sorts of things, and I can't remember from his detailed records whether or not there was a deglaciation in between. Yeah, but that's an interesting thing to think about, whether or not these glaciations were locked in for several 100,000 years, or if there's deglaciation between them. We do think that they were sort of locked in the ice, and because you don't see a lot of erosion on these things, so there's not a lot of evidence for polishing or striations on them. So what we think is you had these high points that were sort of locked in the ice, and the ice was kind of flowing around them and not scouring them too much. Yeah, back.
As you probably know, Mount Curry is dropping a bit of its society. Have you done any research or can you give any added information as to why?
So the Mount Curry, landslides happening on Mount Curry? Yeah, I haven't done any research there, except for hearing what I consider cool stories about it. Seeing as it's not yet gone into a town or anything like that, but I haven't done any research there. I think it's just sort of steep mountains, normal gravitational materials. It's not unstable volcanic material or anything like that. It's just freeze-thaw, weathering, and steep mountains and gravity. Yeah?
When did Mount Garibaldi last erupt?
Mount Garibaldi last erupted 8,650 years ago, I think.
So would that lava landed on top of the ice and then formed the Cheek-Eye Fan when the ice melted?
Right. So during the last waning glaciation, so the question is, would that have formed on top of the ice and then formed the Cheek-Eye Fan as that the ice melted away? So that's the reason Mount Garibaldi doesn't look like Mount Fuji or Mount Rainier, is that it was a supraglacial volcano. So it was building and building and building and started erupting on top of the ice sheet. And of course, that ice sheet, the toe slope support would go away as that ice melted. And so the Cheek-Eye Fan is about a quarter of Mount Garibaldi, has come down into the Squamish Valley. The new development, Sky Ridge development, they blasted away one of our cool outcrops. And what we saw there was this material came down, this new ardent, it's called, a glowing cloud, came down the slopes during those last glaciation and eruption 8,000, 9,000 years ago. And it came down and it hit the ice and it stopped up there sort of above Squamish. And cool things in that deposit are we have blocks, blocks up to this big with little joints all the way around the outside. So more or less jointing going radially from these blocks. And if you pick up one of these blocks and just drop it, it shatters apart. And so there's no way that this block would have maintained its integrity from 2,000 meters elevation down to the valley. So it had to have been hot when it was deposited in the valley. So we have evidence for sort of pyroclastic flows coming down and almost making it to Squamish, but just being blocked by the ice. And so really dynamic, 10,000 years ago would have been quite a time to be around Squamish. Hey, Dean, if I went into that other room, would this thing freak out?
You're going to lose reception out there.
Okay.
Can I go and see if there are questions out there? Shall I? Shall I go see if there are questions?
Sure.
Okay.
I'm just curious, what new technologies are you adopting that's changing the scope of your work? And are there any technologies over your career that are identifiable as key to your work?
So the question is, what new technologies are we seeing and adopting that's changing the scope of the work? And what do we think will be key going forward? And I think this sort of unmanned aerial systems, drones are incredible technologies. The price is coming down. Flying them is not the issue anymore. It's the collection and the use of the data. There's regulations around flying them, but drones are an incredible tool, especially for volcanologists, because Glenn can send his equipment into the fumarole with a drone rather than a grad student. And while it's quite a cool experience, I think that maybe let the grad student fly the drone. And so I think that really sort of the drones, the unmanned aerial systems are getting bigger, they're getting more sophisticated, they're getting easier to fly, and really the payloads that they're able to carry, the resolution on the camera, the sensing equipment, you can see all around the world, they're flying them into volcanoes now, and they're becoming more and more robust. And so I think that's quite a bit of the future. At the Geologic Society of America conference, there were certainly sessions on UAVs and drones and mapping and volcanoes and things like that. So I would say, for me, the technology that I was using in the subsurface on the lakes was sort of fish finder technology, and where it's really advancing and we're getting a lot of joy from is the photogrammetry with the drones. Yeah, thanks for coming. Were there any questions out there? Oh, great, yeah.
You were talking about the hypothesis that the chimney is not a chimney, like the Black Tusk is not a chimney, so is what you're saying is that's all it ever was, versus being a big volcano that collapsed?
Yeah, so the question is the Black Tusk, being a chimney, is that sort of the amount of material that was there? Yeah. Was all it was, rather than a bigger edifice that eroded away. Yes, more or less. We think there's been some erosion with time, but the textures on the outsides are leading us to think that the amount of lava wasn't too much more than you see.
So wasn't there stuff at the bottom that would have made the first theory? I mean, if it collapsed, there would be residue at the bottom?
And that's another thing, sort of, we haven't looked into it in a whole lot of detail yet, but where is that material? Where did it go? And there doesn't seem to be a whole lot of remnant material to create some sort of paleo cone. And so that's kind of circumstantial evidence that backs up our hypothesis, at least for now. Yeah?
Is there any instances of magma flowing through like an ice cave or a subglacial river, like how that would affect how the mountains would flow below it and how the columns form?
Right, so the question is if we have any evidence for lava flowing through an ice cave or a subglacial river. And I think that this example here that's just south of us on the Sea to Sky Trail, if you ever get a chance to go here, it's really neat. It's called the BC Rail Quarry. This spot, the interpretation that this was a lava flow that, based on the jointing orientations, these being horizontal here and all sort of coming to a point here at the top and curving to that point, this has been interpreted as that. So you think of an esker or something where sediment at the bottom of a glacier. Bill Matthews interpreted this as possibly that. With new technology, like LiDAR data in this area, what we're going to try to do is take a look at the LiDAR and see if we can see this sinuous shape throughout the landscape. You see it as you ride your bike or run on the trail there at different spots, and we're going to try to see if we can map that out and see, does this make sense to be a continuous flow?
Do you have a date around these lava flows to coincide with Black Tusk or the origin of the lava?
So this question is, do we have a date and age on these lava flows? And they got some charcoal from the bottom of one of these flows, and they were dated at the youngest being 34,000 years ago. So they're a bit younger. They're thought to be extension-related volcanism, a little bit different than what Black Tusk is, more subduction-related. And so they're sort of in the same ballpark, but not synchronous.
Opalcone and Amper Mountain, Neve, they were all volcanoes.
So the question is, Opalcone and Mamcra Mountain and Neve, certainly Opalcone, were they all volcanoes? And certainly Opalcone, it last erupted around 9,000 years ago, and that lava flow comes down, and that's where Squamish has its aquifer underneath that lava flow. Beautiful system. I'm not familiar enough with Mamcram. I think that's older sort of coast mountain rocks and not younger volcanics.
Did they allow you to throw some medical isotopes in the lake and see when they come up on the creek?
Right. Yeah. So the question is, could I put radioactive tracers in Garibaldi Lake and watch them come out the bottom? I'm not ready to ask that one yet. BC Parks have been very generous to me, letting me stay at the ranger station and use the boat. But one thing we've been thinking about, and a student in my class right now was thinking about, could you just use stable isotopes? So oxygen-18, deuterium, things that we use to track climate change. And could you say, okay, here's the signal, here's the isotopic signal for fresh snow. Here it is for ice. Here it is for the lake water. What is it at Garibaldi Lake? And can we piece together, just from those isotopic signals, which change over time, can we say sort of what is the age of this water, or where is this water coming from? And there's also tritium analysis, which is from nuclear testing. You can measure tritium to tell how long that water has been in the system. And so...
there'll be strontium from Chernobyl. So
that's right. We use these natural, these human disasters to think about natural disasters. Yeah?
It seems to be that there's an eruption in this area every few thousand years. Is the frequency of eruptions decreasing as given the fullness of time?
Let's see here. So the question is, there seems to be a frequency of eruption of a few thousand years, and is the frequency of those eruptions decreasing with time? And so what I'm going to try to find here is a USGS diagram that I've used in other talks here at the end. If I get there, my initial response would be, no, it's not. We don't, sort of over the time span of tens of thousands of years, we're sort of in that. But then you break that down into our time span, what does that mean? And so I think that the frequency of eruptions is not necessarily decreasing. There seems to be more activity in the Cascade Mountains in the US than there is in the Canadian equivalent, and that has to do with some of the plate tectonic situation. And so I think that it would not be surprising if one of these Cascade volcanoes up here rumbled to life. But there hasn't been a systematic decrease in the amount of eruptions. Mount Garibaldi certainly has decreased, but it's still in the right tectonic situation to erupt again. And we see these pauses in all of the stratovolcanoes in the western U.S. with the Cascades. All right, I got one more in me. I'm losing my voice. Got to teach tomorrow.
Any reason behind the keyhole and cable hole? You know the hole in the rock there?
Yeah, so the question is Keyhole Falls, right? That's a fantastic place at Mount Meager. So what happened at Keyhole Falls? Is that what you mean?
No, it's just mean the hole in the rock.
Oh, the hole in the rock at the table.
Is it just the way it's eroded? Or
Yeah, so if you've ever been to Arches or anywhere in the U.S. Southwest, okay, so you have these big arches of sandstone. It's the same process. What you need is a fin of rock, and then you get erosion perpendicular to that fin, gives you an arch. So essentially, the orientation of this dike in the table was sort of making that fin. As it eroded and got thinner, then you had erosion, sort of normal freeze-thaw erosion through that, and it made a hole, and you get an arch. So a very different rock, but a similar process. All right, thank you very much, everyone.
Hello. Hey. Thanks, Dean. Thanks again for being here. Thanks to the RMOW for supporting this event. Thanks to Dean for your hard work in the booth. And if you know of somebody who could not be here tonight, we do have a recording of the event. We're going to be posting it on the Whistler Public Library Facebook page. That'll probably be the best place to find it.